titrations?
They are a laboratory procedure for quantitative analysis.
They are used to determine many things,
like the concentration of an analyte in a solution, the stoichiometry of a reaction,
the number of electrons gained or accepted in a redox reaction, or the solubility of products.
Why do we perform them, and what do we need to know before performing them?
Great question. In this experiment, they are used to determine the concentration of a solution by reacting it with a solution of a known concentration.
This is done by carefully adding the known titrant to the unknown analyte until the end point.
The end point is when the reaction is complete. This is observed visually when the indicator turns a light pink.
The unknown concentration can be calculated based on the volumes of both solutions, the balance equations, and the concentration of the known solution.
How do we read volume?
Read from the bottom of the meniscus at eye level and report to 2 decimal places for accuracy.
Before you start your lab, make sure that you're taking all the proper and adequate measures to protect yourself and be safe. We can get started with the lab.
We need a solution of potassium hydrogen phthalate, better known as KHP. First,
we zero out the scale with the weigh paper.
Accurately weigh a 0.05 gram sample of KHP and dissolve it
30 milliliters
in
of
a water
water.
flask. We will need 3 flasks of this KHP solution. The KHP solution is our known solution for standardizing the NaOH.
This is the mass of KHP into 3 flasks.
After preparing the 3 flasks, add 1 to 2 drops of phenolphthalein, which will indicate the equilibrium point for the acid.
We must prime our burette to ensure accurate measurements by removing contaminants and to prevent dilution of the solution being used.
Start by ensuring that the stopcock is horizontal, then add a small amount of water and swirl it around the inside. Do this 3 times and drain through the tip by changing the stopcock to the vertical position.
After rinsing with water, prime the burette with NaOH. Do this by adding a small amount of NaOH and tilt and rotate it to coat all inner surfaces. Then drain the solution. Repeat this process 3 times.
Place the primed burette in the clamp in a position where the desired volume is at eye level. When adding the solution, you should not be adding it above your head.
Add sodium hydroxide to the burette. For the duration of each trial, sodium hydroxide should not be re-added to the burette until the titration is complete. If more is added, accuracy can be compromised.
To avoid this, one should fill until the 0.5 milliliter marking on the burette.
Before recording the volume, drain a little solution or flick the tip to get rid of air bubbles. Here in trial 1, we have an initial volume of 0.48 milliliters.
Now, use the burette to slowly add NaOH to the KHP solution.
Swirl the flask to make sure it is uniformly mixed. Continue adding the solution until you reach your faint pink endpoint. The final volume is 22.98 milliliters, meaning that 22.50 milliliters were delivered. Repeat this process at least 2 more times for 3 trials to ensure accuracy.
Once the faint pink endpoint has been observed, record the value shown on the burette to 1 degree of uncertainty. Subtract the initial volume from the final volume to find the total volume of NaOH delivered to the flask. Since KHP and NaOH are both monoproctic, the ratio between the moles of hydrogen ions in the acid and the moles of hydroxide ions is 1 to 1. Next, take the moles of hydroxide ions, approximately 2.45 times 10 to the negative 4, and divide it by the total volume of the NaOH solution. This equation gives us the molarity of the NaOH solution.
For this exercise, we will find the molarity of citric acid and soda with the now known molarity of NaOH. The soda was thankfully prepared for us already. Add 25 milliliters of soda and 25 milliliters water into an Erlenmeyer flask and add a few drops of indicator. Fill the burette with NaOH until the 0.5 milliliter mark. Add NaOH to the flask and swirl it until a slight pink color. Once the faint pink endpoint has been observed, record the value shown on the burette to 1 degree of uncertainty. Find the total volume of NaOH delivered to this flask. Since citric acid is a triproduct acid, the mole ratio between it and NaOH is 3 to 1. Therefore, divide the moles of NaOH delivered to the soda by 3 in order to find the moles of citric acid. Next, divide the moles of citric acid by the total volume delivered to find the molarity of citric acid in the soda.